This presentation is for Computer Science 2, COP 3503. It covers Section 1, Introduction to Algorithms. So let's say a few things about algorithms. The first is that they must be well defined. The second is that they always have some sort of input data or input set. This might be, say, a list of numbers that must be averaged. It might be, say, 2 or 3 numbers that are multiplied together. It might be a list of bank transactions, a list of words, a text document that needs analysis. So input values can take a number of forms. There's always a set of output values too. This might be the result of multiplying numbers together. This might be a sorted list. It might be the average of a list of numbers. It might be, say, some sort of a trend from numerical data. Algorithms can solve a well-specified computational problem. And this is maybe things such as predicting the outcome of the stock market. It might be finding the average frequency of some audio data. So any kind of well-specified computational problem algorithms can solve. For a well-specified problem, there should always be a clear relationship between the input and output data. This means that given any set of input data, the output data would be predictable and known. So we'll start off by talking about the sorting problem. And in this case, our input will be a sequence of numbers. Now, to sort, you could actually have a list of, say, words. You could have a list of times and dates. But for this discussion, we're just going to have a sequence of numbers. The output will be a reordering of that sequence. So here's an example where we're going to provide a sort to an ascending order. The input sequence is 31, 41, 59, 26, 41, and 58. The sorted output sequence is 26, 31, 41, 41, 58, and 59. So let me just point out that this example is known as an instance. Instances are usually uniquely identified by a set of inputs. Now, it might not seem like a very important point right now, but later when we talk about object-oriented programming, instances are a very vital concept. So a little more on sorting. The use of sorting is pervasive in computer software. You can't see any kind of a user interface object or list without multiple ways of sorting, such as name, time, date, and so forth. There are many types of sorting algorithms out there. The book and this course is going to focus in on 4 of them, but there are quite a few more than 4 out there. In fact, it seems like almost every computer scientist wants to create their own sorting algorithm. So we say that algorithms are correct when the output for any given input maintains the expected input-output relationship. That's what we were discussing in the previous slide. We always need to make sure that the relationship between input and output is predictable. A correct algorithm solves a computational problem, such as averaging numbers, such as finding maybe a root mean square of a set of numbers, and so forth. There are some incorrect algorithms that are useful when their error rate can be controlled. So there are some pretty common examples of that. For instance, JPEG images take an original image and introduce, they actually degrade the image in certain ways, but if you don't degrade it too much, then your perception can't even notice the difference. So that's a time when you keep the error under control, then the resulting photographic image still looks good. There are lots of audio algorithms too that degrade images, but not that your hearing can recognize. MP3 files, for instance, is one really common example. The book in this course uses pseudocode a lot. The purpose behind using pseudocode is not to confuse you, but it's to provide an opportunity to make the algorithmic idea as clear as possible. Pseudocode many times resembles languages such as C and Pascal. So if you know any languages similar to C and Pascal, the pseudocode is not going to be a problem for you. Here's an important point though. You can transfer this whole idea of clear intent expression even to real source code. The mark of a great programmer is when their source code is easy to read and understand. This will be covered in more detail in the Programming Languages course, but it's a very worthy goal to make your source code as readable as pseudocode. People should be able to look at your source code and understand what it does. So keeping with this theme of sorts, we're going to talk about the insertion sort. Insertion sorts are efficient for small number of elements. Later on in this chapter, we'll talk, and especially in chapter 2, we'll talk about how insertion sorts really get very inefficient when the input data set gets large. But for insertion sorts, as an example, let's consider 5 playing cards that are face down on the table. As the cards are picked up one at a time, a decision is made where in the hand it should go in order for the cards to be in ascending order. Okay, let me pick my first card, the Jack. Next card, Ace, does not go here, but will go there. The Queen does not go here, but will go there. 10 does go here, and the King doesn't go there, doesn't go there, doesn't go there, but does go there. Now the cards are all sorted in ascending order. Okay, the insertion sort. So we have an array of numbers, and the array can actually be sorted in place, which means we don't need a second destination array. So the name of this function is going to be insertion sort, and it takes as a parameter an array named A. So what we're going to do is start off by counting from J equals 2 to the length of the array. And the reason we don't start at 1 is because, just as I showed you with the card sorting, we don't need to sort the first card. It's already by itself. Okay, and one thing to point out is that pseudocode starts at 1, whereas most programming languages today, such as Java and C++, start off at 0. So we set a variable called key equal to A sub j. That's whatever the current element we're looking at. And this is a source code comment. We're going to insert A sub j into the sorted sequence. So we set a variable I equal to j minus 1. And we're going to do this until we find the appropriate place to insert the value. That's just like in the card example I showed you. Sometimes we inserted it right away, or sometimes we had to move down the line before we could find the one to insert it in front of. So here we set A sub I plus 1 equal to A sub I, and we set I to I minus 1. And finally, we store the key, the new value. So that pseudocode can actually be easily converted to C code. And I have a code example on the code example page. If you go to cop3503.ricklineker.com/codeexamples.html, you can find this very source code. Okay, so I've run Visual Studio, and I've got the C++ program open, the source code, and you can see my insertion sort function right here, and it identically mirrors the pseudocode that I showed you. And I have this little support program or support function called showDataArray. Now, here's the data list we're going to use. Notice it's not sorted. We're going to call this method, this function that shows the unsorted data list. We're going to call our insert function, and then we're going to show the data array again. So we run this, and as you can see, the unsorted list and then the sorted list. Simple.